All right. Who knows what this is about, this DEX stuff? One person, two, kind of, some kind ofs. All right. Let's talk about smart file importing. So far, the project has been named DEX. That kind of stands for data importing and exporting, so data exporting. There's a whole bike shed thing of like talking about the name. Since we chose that, a number of people have brought up that, hey, there's a lot of things called DEX, so maybe this shouldn't be called DEX. You can weigh in on that bike shed. I don't want to think about it. There's a thing called multi-DEX that I saw, and that's pretty cool. You know, this thing has a. You can go and read the spec here. Nope. If you search for it, it'll be there. And so there's a kind of rough spec here that talks about what layouts are and what splitters are. We're going to talk about that in a moment. And then talks about the kind of architecture of what we're talking about and how to plug it into things. It's very, very basic. And this has been, part of the IPFS goal for a long time. And the benefits are truly massive for a lot of use cases for IPFS. We just didn't have time to work on this. Haven't had time to work on this for quite a while. Other things took priority. But it's really time to revisit this. This is, as I hope to convince you over the next 10 minutes that there's a lot of really strong promise to this, and that if we prioritize this for the next quarter to quarter or so, a lot of things will get faster and better, and a bunch of use cases are going to open up. So we'll kind of dive into that. But let's start more basic than that. So when you add, this is imagine adding some stuff to IPFS. You get a bunch of hashes. And if you're doing normal IPFS add, this is UnisFS, and you're adding a bunch of, so there's like the lower level IPLD hash-linked graph, and then on top of that, we're modeling a Unix-like, a familiar file system. We'll hope to actually get POSIX compliance someday. Or maybe not fully POSIX compliant, but at least getting permissions in, right? The point here is the file system stuff. If you haven't gotten a chance to dive into this kind of stuff, the IPLD work came out of really thinking about a lower level primitive than files. Turns out files wasn't the right thing to base all this on. And so all the IPLD work has been trying to take a project in flight and then like rebase it on top of a new, better heart. Because really thinking about structured data at a lower layer makes a lot more sense, and you can easily turn that into files, and going the other way around is quite clunky. Think about APIs in the world of Web 2.0 world. It's all structured data. You're not moving around a bunch of files. I mean, yes, you are, but like not your logic. So a lot of the DEX stuff is file specific, but it does present a lot of opportunities for other kinds of data. And so the goal is to maybe motivate it with files and maybe nail that, and then think about other kinds of data structures. So in a normal Unix file system, we have directories and files. Directories are DAG nodes, files are DAG nodes, and we take a big file and chunk it up into a bunch of pieces. So this is a graph of this directory, I think. Maybe not. Yeah, I think it is. And you can see here a bunch of things, right? Like you can see a directory as an object, and it's pointing to some objects, and right there's a file that happens to be big enough to point to 4 other subblocks, right? So a big file is getting chunked into smaller pieces. If you had a really big file, this would go on. Now, how you do that, this is a standard file systems technique. How you choose to chunk a file and lay it out has vast implications for the performance of your system and vast implications for the use cases. So we'll get into that in a moment when we start talking about layouts. But the structure of the graph is what we mean by a layout. So when we take a file and import it, and the graph that we construct out of that will have some shape. And that shape we call that the layout. There are a bunch of different things. You could have a balanced tree, but that might have a problem. What sounds like a problem if you have like a normal standard balanced tree? What would happen if you start trying to play a video and you have like the root node in the CID and you try to play a video? What would happen? So it sounds like it's not going to be fast enough. Why? Time to first byte is affected because if you have a really nice balanced tree, you're going to go and try to seek to the first byte, and you're going to go down a bunch of levels, and you find the first block, and then start streaming that in. So actually having a lopsided tree where the very first node immediately points to data, that is way more efficient for normal files. This has been around in IPFS. It's not a default, but if you pass in add-t trickle, it does this for you. But other kinds of files might want different layouts. That nice trickle structure makes sense for things like video, but there might be something else that you might want to do. So that's what layouts are about. And now the other stuff that goes into this is starting to think about potentially being able to deduplicate data in a much smarter way. So think for a moment of you have two files, and you change one segment in one of them, and maybe you insert a single character. Now, in a normal naive size chunker thing, then the rest of the file is going to be different, right? It's going to chunk to a different set of hashes. I'll show that in a moment here. So if you have suppose that you chunk a file and then you make a change in say C3 or something, you insert a single character. Now, when you go back and re-chunk that and hash it, now C3, C4, C5, C6, C7, all are going to be different. So that sounds kind of dumb. Turns out that we've known how to do better things than that. There are techniques for figuring out just very simple ways of getting deterministic chunking to happen based on the content itself. And those things, so Raven fingerprinting and Adler32, I think cyclic hash functions. Is it cyclic? Forgot the wording. But there are specific kinds of rolling hash functions that when you apply to a file start yielding certain numbers, and you can come up with an algorithm to kind of choose chunks such that if you were to insert something to C3, maybe C3 changes, maybe C4 changes, but the rest would be, a large subset of the rest of the file would be chunked exactly the same way, so that you get the same kind of nice properties. So this, a lot of people have been doing this for a long time. This is also in IPFS. It's you can pass a special chunker, Raven fingerprinting, and it'll do this. Myth about IPFS: Raven fingerprinting doesn't help. Total myth, and I'll show it. It does help quite a bit. It just creates really small chunks, which was slow for a while, but now with Badger, it's fine. You could also choose not to do any chunking at all, and that's what Git does. Now, what would happen if you do no chunking at all? Yes. What else would be true? What happens if you have a file that is a gigabyte large and you change one character? Yep. So, womp womp. Don't do that, right? So it's 2005. LBFS was 2001. You should go back to the past. Turns out that this is one of the reasons a lot of people have trouble with Git in really large repositories is because of this. It doesn't handle things like video and large assets really well at all. There's a possibility that if we get this importer stuff to be really, really good, it could someday make it back into something like Git. There's been conversations about that. So we do some of this Raven stuff. Now that's kind of a general purpose thing of saying just whatever data you throw at me, I'm going to come up with some algorithm to try and chunk it intelligently. Raven fingerprinting is one version of this. rsync does something similar with Adler32, I think is the function they use. There are other things what if we knew something about the layout of the file? So for example, I think let's see. I'm going to create a bunch of random files. I'm going to compress them. Is that right? I think. Yeah. So if I just add that, that's not going to be very nice. But there's a special command in there, which I think is tar. I think, is that what it is? Yeah, I think so. So what that did, it's a very special case thing, is that it imported the tarball smartly. It looked at the headers of the tarball and created specific objects for it. And I'll show you the difference between the two graphs. So graph MD, if we look at this one, oh, come on. Great. Is that there? Oh, whoops. Forgot to pass it to, no, that should have worked. Oh, I guess there's only one object. It's so small. Here, let me create something much bigger. There we go. So this shows me the underlying, it's a tool that I wrote, I'll demo it later. It shows me the underlying graph that IPFS generates. And so we can visualize that. And so this is like the graph, right? So these are like the underlying file blocks of the tarball. This is an intermediate node. So this is a balanced tree, right? So this is like the root node, and so on. So it's not a perfectly balanced tree, but it's built that way. If we were to add it with a different thing, like add, this is the trickle thing. We're to do the same operation. I'm going to refresh this, then you get a different shape. And so what's going on here, whoa, that's a lot of data blocks in the first one. Really trying to optimize the first few blocks. Huh? So that's a bunch of objects in the first one, and then the very bottom one happens to be an indirect block. You might have more indirect blocks. I think like XT4 has like 4 or something. Like there's a whole bunch of research into what layout might you want to optimize in certain kinds of file system use cases. But the tar one, and so this is what's kind of cool about this. If we now visualize a tarball version, did this work? Oh, whoops. Yeah, it's somewhere up here, right? Making sure you're following along. OK, so what happened here? So there's like a way of adding the stuff such that the tarball headers themselves are single IPLD objects. And so if we were to like look at this thing, if we like were to cat that, oh come on. DAG, maybe? Yeah, there we go. So what's in there? There's, some data is in there. This is the tarball header stuff, surprisingly large. Might be some other stuff there. But that's just IPLD stuff. If IPLD was smarter, which the goal is to get there some way, you would be able to see transparently this data right there, and you'll be able to see like the structure within it. And that's the motivation for IPLD. It's like, don't have to, IPFS should get smart enough to be able to understand those internal data structures. But that's where the tar header is, and the actual data is in here, right? So the actual data link, if we were to follow that data, then that's the actual like data of that file. And so why might this be useful? Does anyone have ideas why importing a tarball this way might be useful? Yep. Yep. So one thing you might be able to do is, knowing that it's a tarball, you could like seek into the tarball into a specific file and just pull that out, right? And so when you were like, if we want to see this specific thing, I think we can actually do this here. Let's try it out. I don't think I've ever tried it, but let's do it. So if we take this, this might not work because I think it's expecting. We can probably do it with this. So if we get this out, then we like walk into. That's because this is using the protobuf stuff, not the CBOR stuff. If it was using the CBOR stuff, we could like traverse this much nicer. Let's see, I think it's link 0. I don't know. But the point is, you should be able to traverse into that graph and pull out a specific file. So that's one thing. The other thing is, what if you have 10 tarballs, all of which include the same file? If you chunk it with a normal standard way, and IPFS is not understanding this tarball, it's just going to chunk it its own standard way, and maybe it'll get lucky if you use rapid fingerprinting and align and maybe duplicate stuff. But chances are it's not going to. If you do it with smart tar importing, then immediately it will deduplicate the same. Whenever there's a tarball that happens to include the same file, it'll deduplicate that exactly. Now, where do you know there's a lot of tarballs that have the exact same contents? Releases. Releases of what? Software. Package managers, right? So think of an NPM or apt or something like that. How many packages include the exact same code? Think of like all of the versions of your package, right? Like all of them right now in NPM, they're sitting like a whole different tarball. And so like, think about deduplicating all of that. That's not just useful in storage, it's useful in bandwidth. If you were using IPFS to pull down the NPM stuff and you're pulling down package X, then you might not need to pull down all of the tarball. Ever wonder why NPM is so slow? That's why. One of the reasons. So that's very promising, but it needs like this smarter importer stuff. There's a bunch of stuff to figure out there. What other kind of package manager includes a set of files that are all very similar? What other kind of package managers do we have? So I guess like binaries might have underlying, like huge binary programs. Some package managers have binaries that are quite large. They're megabytes in size. But when you look at the internal structure, they have a lot of duplicated stuff, and you could deduplicate that intelligently. You could deduplicate libc out of most package managers like right away. Maybe not, because I think like the linker might change the addresses, but there's some winnings to be made there. The other thing that it could massively deduplicate is things like Linux ISOs. So imagine if you ran the Ubuntu or Debian, ISO installer system, and you have like hundreds of ISOs, and all of these, are targeting different architectures and different versions and whatnot, and you have to like keep all of these around. And in reality, that ISO, which is probably hundreds of megabytes, includes a bunch of files that are exactly the same, version after version after version after version. And so if you imported an ISO smartly, you could look into its internal file system and deduplicate that intelligently. So then having another ISO would just be the changes. So that's the promise of this kind of stuff. And there's a ton of things like this. A lot of files that because of how Unix and computing evolved, we ended up using just files and moving around files as the native like bundle of data. And turns out it usually is full of the same stuff. So let me give you an example. I make a lot of presentations. I reuse the same images. Images are large. So, if I go to Git talks, so I have 8 gigs of Keynote files. And this is just a bunch of IPFS docs. And if I think, let me see if I have it still running. Run this too. So what I did here was I have a tool that allows me to test the differences between certain different repo types and the importer that we're using. And let's check out the size of importing with a normal size chunker, and that's 7 gigs. They duplicated some stuff. Like, that's pretty random. I'm kind of surprised. That must be like the exact same files or something. Otherwise, it would be really difficult to get that lucky. But then let's look at Rabin. 2 gigs. So I just imported a bunch, and then this is just like the naive, like the not fully naive sized stuff. This is like the general purpose Rabin fingerprinting thing. It just, saved me 4 gigs of stuff of just without knowing anything about Keynote. Now imagine if it knew something about Keynote and how it represents its own internal files. This could get chunked drastically better, right? So this is like the promise. There's a whole bunch of different kinds of files that we can learn how to chunk. And so the goal of the project is to come up, so of like this DEX thing, is to come up with like a general way of attacking this problem, because there's a ton of different files out there, and you don't want to have to implement special chunkers for everything, but you want to structure a project such that when somebody needs to create one, they can, and then they can benchmark that against doing the naive thing. Or people can put research into some of these like rolling hash function stuff and see if they can get that to work even better. And so the idea was to come up with like this structure for saying, let's rip out all the file importing stuff out of the core implementations of IPFS into a different set of modules, and have a set of programs and libraries that know how to import files. So they consume a file as an input and then output an IPLD graph. And so then you can think about how to configure that chunker to tune how that works, and then IPFS would import that as a library and run it locally. Maybe some other implementations might actually call out to a different program or something. But that's then we can make that pluggable so that people can like file pull requests against that and say, hey, I just came up with a way to import Keynote files, and here you go. Or hey, I came up with a way to do ISOs, here you go. And so that's how we can scale this. That's how we can, and ideally we would do it in one language as opposed to having to do it in a bunch of different languages. But that gets into the whole question about like WebAssembly and whatnot, and like what's going to be the winner. But for now, like we could just follow the same structure, do what we do with everything else, which is implement it in 2 languages, and see how it goes. And so we have some of the basics already. We have this like layout stuff. We have some of the chunkers. We have like the tarball thing. But we want to do a lot cooler stuff. I think the ISOs thing is very promising. And I think getting it to work really well for package managers is also really promising. So if we treat those as like the short-term use cases and go after them, then we can potentially speed up a ton of stuff. Earlier this morning, we were talking about potentially doing this for JavaScript CDNs. So think of it like a CDN with a huge bundle of JavaScript in there, like jQuery, like every version or whatever is just pretty big, has the same stuff. If you could intelligently chunk that, like rip out the modules that are the same, or like a bundle, like a Webpack bundle, rip out the modules that are the same and like import those that way, so you don't have to like bundle the same stuff all the time, right? And so this is there's a bunch of interesting work here. I think the way in which we can reboot the project is by forming a working group. And so the way to think about that is first identify the use cases and the people that might be interested in that, and the projects that might benefit from it, and then see whether we have bandwidth to do that in the short term or we keep putting it off and whatnot. But this is going to benefit IPFS, so both implementations. It's going to benefit cluster because it's going to be able to more intelligently understand the data that is pulling in. There's a tool called IPFS Pack. I don't know if you've ever seen it. It's an experiment around data set distribution. That already has a way to describe the importers that you're using so that we have a little description so you can always take the same file, apply that description, and output the same graph. So that as importers change over time, you can always return the exact same data. Package managers, ISOs, containers. So it turns out that a Docker container is just a bunch of tarballs smashed together, right? A lot of those tarballs often contain the same stuff. Sometimes there's tarballs inside tarballs. So I don't know if you've ever played around with container images, but there's just a bunch of tarballs inside. And so if you were importing them smartly, then you could duplicate a ton of this stuff. And then maybe you could shrink down the whole container, Docker Hub, I think it is. You could probably shrink that drastically. And then you wouldn't have to pay tons of, think of all of the bandwidth that people are spending by just, in CI especially, just downloading the same images over and over and over again. The same bytes are moving. This is ridiculous. And you can then start to see how this could get even crazier. Once you start doing this, you can think of an entire OS or running a VM on top of something like this, or being able to understand the internal data structures of you have a VM image, so not just an ISO, but an image of a running computer, and then import that intelligently, and then understand what the internal state of it might be. And do migration of processes, all of the process migration stuff. I don't know if you've ever seen some of that work, but it's a live running system with a hypervisor and has a VM running, and then something happens and there's a slightly older snapshot of that VM, and they want to migrate that process somewhere else. This is used a lot in cloud. Being able to do that, this kind of stuff wouldn't even apply there. And yeah, we talked about media. And then you get into a very interesting one, which is once you have all this chunking importer stuff, you could start putting functions in there. So imagine applying a filter to an image or something. And the way you express the filter is not by taking the raster image, applying the filter, and then rendering it, but taking the original image and attaching a filter to it in code, and then shipping that. And then the user runs that. And so it's a file. It looks like a regular file. But if you can intelligently execute the code before it comes out of IPFS to the user, then it would feel like a file exactly the same way as everything else, which is it'll output the bytes all the time. But it's stored in a very different way underneath the hood. So that starts suggesting a whole bunch of other things that we can start doing. We can do compression this way. You can do encryption and decryption this way. I had a little random hack before where I have a compressed file and I have an IPLD object that points to the compressed file and points to a key. And then I mount that, and I see the file unencrypted. And every time I write, it writes encrypted into IPFS. So that's where a lot of this can go. But there's some important roadblocks to get there, which is this how do we lay all this stuff out and so on. So yeah, I think I'm going to pause here because I think we're already going into lunch and I'm holding you back from food, and I don't want to do that. So I'm going to take questions, and then if you're interested in looking more into this and might want to join a working group on this, let me know, and then I'll see about whether or not we can form a working group for this next quarter or the quarter after that. Great. Any questions? That's right. So I do envision a set of sane defaults, but it is important that we always are able to go back to exactly the same file. And this is where the IPFS back stuff got, it was pretty important to come up with, I don't know what it's called. I think it's a format string, I think. So this defines, so this would be part of the DEX project. It would be like a string. It's just a string that defines what configuration options are involved, so that you can take the exact same file and produce the exact same output every time. And then, if you want to upgrade from there, like that's totally sane. And so then this could be fed into, so the IPFS add thing could be enhanced to include, you could specify the string if you know what it is, right? Instead of specifying these other options that are there. But I think over time we could get to the same defaults, but through benchmarking. A lot of that it should be, rigorous benchmarks that show, hey, when you do this, videos get better. Yep. Anybody else? Other questions? Yep.
You mentioned the opportunity of getting this back into Git. What are the roadblocks there?
So I think probably the biggest roadblock there is more social than anything. I think it's just demonstrating the stuff and then coming up with something that seems palatable to the Git community, where Git would have to learn how to deal with files that are chunked internally. And so that would require thinking through that. The Git internals aren't that complicated. It's a pretty good structure. And so this is pretty feasible. It's just a matter of thinking through the impact of a bunch of the tools that assume that file is always a single file. And I would imagine that a lot of those tools would expect that you would unpack like the compressed representation into like this like normal standard files. They would just kind of expect that to happen. But yeah, I think this would be quite a significant effort, but I think it would definitely be worth it to cover a whole bunch of use cases where suddenly you should be able to use all of the tooling that works with Git versioning and commits and so on, and apply that to versioning really large data. Right now, it's not easy to version really large data. It still sucks, right? Like people have been working on this for many years, and it's still terrible. And so a lot of the tooling around Git is really nice, and a lot of the stuff that people have built in terms of GitHub and a whole bunch of other tools is also really nice. It would be really great to be able to reuse all of that with versioning for large data. But that becomes a question of how do we do it? What does the pull request really look like to Git that says, hey, we're going to add all of the support? And I think the biggest part is convincing that group that this is worthwhile. And that would just be with really hard facts of saying, look at what Git could now suddenly do. Yep.
Yeah, on that earlier slide, you had complexity up there, and that one fits into this conversation, representing data as generating functions or complexity of generating.
Yep.
And that just kind of has me thinking that one possible version of this involves maybe a total language.
Yep.
Stores transformations on data, and you can publish those up in IPFS. But then obviously we have kind of this IPLD thing going, and this idea of structured data. And I was just kind of wondering if you have any thoughts about where you draw the line between kind of structured data that's interpreted versus code, straight up code. Well, yeah, it's really interesting.
Code is data, right? And data is code. So I think for those unfamiliar, the IPLD effort is diving deep into computation. So it turns out that a lot of the ways into how to improve data distribution is actually, and applications on top of it, is to really rethink how we mix computation and data. And so you can read, there's a whole bunch of notes here that talks through use cases, that talks through potential things, bunch of different discussions. I think probably the most valuable thing that we've gathered together here is this awesome bibliography that you can dive through. There's a bunch of really great papers here, and a lot of this stuff is much more about computation than data. And so I don't know if that'll all remain under IPLD. That might yield a different pop out a different project or something. But yeah, so I think a lot of it does become really thinking through just how we represent files in the first place. Why are we storing just byte streams? Why aren't we thinking about storing code instead? And so on. And in terms of languages, there's been some work on this. So there's a set of issues. Actually, it's funny because I was writing an email about this today to somebody who is working on a thing called Kolmogorov blocks, I think, or Kolmogorov blocks or something that talks about doing exactly this. And so, one example would be, so this stack stream thing is part of the IPFS set of explorations, and the idea was come up with a very simple language that would combine other objects and yield stuff. So a normal file would concatenate its children, right? So it would a file would link to sub-files, and it would concatenate those, plus its own internal data segment. And then you could write a single function that represents that. And then you could ship. So this is where the IPLD stuff happened, where we didn't want to start writing that as special cases into IPFS. We didn't want to have to be like, oh, this is this really cool idea. Let's have this code thing in a different language and include it along with GoIPFS. It'd be really nice to have a VM here, like a WebAssembly VM, and then point to the code itself as IPLD objects, and then apply the function on top of another thing. So what this would look like, a file, would be a function invocation that it also points to the code itself, so it knows how to interpret itself, and then it would point to the data, and then that's how you would then stream out the file. Exactly. So all of that. So there's something amazingly elegant and powerful lurking there, and we've been exploring those branches of things, and we found pretty good ways of representing these things. And I think where we're blocked is actually time. I think a number of us are just so spread thin that we can't do all of this exploration all at once. I think Steven, for example, is somebody who has already figured a lot of this out and just wants to build it, but then needs to maintain GoIPFS, right? So. Well, so I mean, this is definitely an open call to help out on the IPLD team, because and come to that right after lunch. We're going to have a discussion about that if you want to hear about IPLD, because there is a lot of really valuable things that can come out of this. And so the importer stuff is, the IPLD primitives are there enough to do the importer stuff without thinking very much about that. And then but at the same time, we can continue those explorations and then yield something much more interesting, right? So we kind of want to stage this where we want to provide the shorter-term benefit in terms of the very simple kind of chunking and splitting we can already do. And then later, once we think about computable files, then that opens up a whole bunch of other possibilities. And so, yeah, I think there's a very interesting, bright future ahead for computing and how we represent stuff. We have to chart a path through all of the possibilities and then start doing some early as we get out. But yeah, hopefully, we can start reducing the vast amounts of data out there, because in reality, a lot of it is just junk that's duplicated. Other questions, or we can release you for food. If there's people wanting to talk about this extensively, you can stay. Otherwise, we'll call it done. And see you around. Thank you. And yeah, if you're interested in the working group, either people here or if you're watching this video in the future, talk to us.